11.45, a certain amount of a gas at 25 degrees Celsius and 0.8 atmospheres contained in a vessel. Suppose that the vessel can withstand a pressure of no higher than 5 atmospheres. How high can you raise the temperature of the gas without bursting the vessel? So here we have a gas in a vessel, and we have a certain amount of gas. What's responsible for the pressure? When I measure the pressure of a gas, what's causing that pressure? Temperature is necessary to cause pressure. Kinetic energy, right? So that's temperature is a measure of the average kinetic energy. It's the kinetic energy or the temperature causing the gas molecules to move around and collide. So ultimately it's really the collisions of the individual gas particles on the inside of the container. But if you had zero temperature, they wouldn't be moving, so there wouldn't be any collisions. So you wouldn't have any pressure either. But so it tells us the pressure that's created by all of those collisions. And it also tells us the temperature. So if we were to lower the temperature, we would expect, on average, the particles would be moving slower, so the collisions would be less forceful, and so the pressure would go down. But if we raise the temperature, then the pressure would go up. So 25 degrees Celsius, we have to convert that to Kelvin. All of our gas calculations require the unit for temperature to be Kelvin, and that's because Kelvin is an absolute scale. Since the Celsius can give you negative values sometimes, or 0 degrees Celsius is reachable, if you plug that into the equation, it throws off your numbers. But Kelvin is an absolute scale. That means Kelvin, the number for temperature in Kelvin, actually relates directly to the average kinetic energy. It's an absolute number, right? You can't go below 0, so it tells you how much kinetic energy really is there. So the question is asking, how high would we have to raise this temperature to get the reaction to burst if the maximum pressure is 5 atmospheres? Because if we get to 5 atmospheres, the integrity of the vessel cannot withstand and it will burst open. Right, so as we said, that pressure is due to those collisions. So if I get enough collisions occurring hard enough, then it will break the container. So what temperature do I need for that to happen? This is a bit of a tricky question because it really only gives us information about pressure and temperature. It doesn't tell us anything about the volume or the moles, so we can't really directly look at just plugging in to PV equals nRT, which is what we've mostly been doing so far in these gas calculations. First of all, is the ideal gas law appropriate to apply here? Is the gas going to be behaving ideally and following the kinetic molecular theory? We talked about this at the end of class last time. Where is it going to be deviating from ideal behavior? So what we said was, to deviate from ideal behavior, you would have to have a situation where the gas is not following the kinetic molecular theory. So you should review that kinetic molecular theory and know it well. The kinetic molecular theory says for a gas to be ideal, the gas particles have to be independent of one another. So they're not close together, attracting. They're far enough apart where they're bouncing around, and when they collide, they just bounce off with the same amount of energy they collided with. So they have elastic collisions. They're not close enough or slow enough to form any attractions. And the space inside the container is mostly empty. The gas, relative to the total volume of the container, the gas takes up a negligible amount of space. And what we said is most gases will behave like that, which is why we use the ideal gas law and why it works so well. However, if the gas deviates from ideal behavior, that requires that we slow the gas particles down so that when they actually do come close to one another, instead of just bouncing off, they may form attractions and kind of stick together a little bit. So any conditions where the gas, you could imagine the gas starting to behave more like a liquid, that's when you're deviating from ideal behavior. That's when you have to use the van der Waals equation instead of the ideal gas law. So that occurs at lower temperatures or at a situation where you have a lot of moles packed in, and you've packed in so many moles into a small amount of space that the particles are forced to get next to one another more, and they're trapped and they get close enough to form significant attraction. So in this case, we just have room temperature, and we don't have a super high pressure, so it doesn't suggest that we have a whole lot of moles in there forcing close together. It's just normal conditions, just regular conditions. So standard temperature is 0, and we're above that, so a higher temperature should help the molecules move faster and be more independent, so that suggests it should be ideal. And standard pressure is 1 atmosphere, so whether we're at 0.8 atmospheres or 5 atmospheres, it's not a huge difference. So we're not going to be deviating from ideal behavior significantly here. So we could use the ideal gas law. The problem is, though, we don't have any information about moles or volume. Should the ideal gas law work at both 25 degrees, where I have a lower pressure, and also at whatever temperature gets me into 5 atmospheres? Is the ideal gas law going to be applicable at both of those conditions? Sure, it should work in both cases. Because, I mean, I'm not lowering the temperature or putting more moles in to the point where the particles will start to move slower and attract more. I have too many and they can't avoid getting close together and attracting. So it should be ideal regardless. Yeah, so what we're going to do here is we're going to set them up as a proportion, a temperature-pressure proportion. And the reason that works is because the pressure-temperature relationship should not change from one condition to the next because we're not deviating from ideal behavior. So if we think about what we want to do here, since there's no indication that the number of moles is changing, and there's no indication that the volume of the container is changing, the only thing we're doing here is increasing the temperature and seeing what effect that has on the pressure. That's what you're doing in the lab. So you should have already at least had some time to think about how you want to set that up experimentally. Well, here we have a very similar situation. We're varying the temperature to see how it affects the pressure. Or actually, we want to know how much of a temperature change we need to get a certain pressure change. But that relationship in this situation is very similar to what you're doing in the lab, because you have a container where the volume's not changing, and you have a number of moles in there that's also not changing. So if the volume and the moles are constant, and also the value for R is constant, we can rearrange this formula and get all our constants onto one side of the equal sign. So if I divide both sides by pressure, and then divide both sides by R times N, I'll have the ideal gas law arranged in that format. And what we said is, throughout this experiment, the gas should be behaving ideally. So at the lower temperature, maybe I'll call that condition 1, the volume, moles, temperature, and pressure in condition 1 should be equal to the volume, moles, temperature, pressure. I mean, the equation should still work at the new temperature and pressure. So since this all is constant, that means whatever the volume over the R, and it's not changing, right? I'm not changing the number of moles or the volume. So when I'm dealing with the new conditions, they should be equal. Right? If they're not changing, oops, it should be a 1. The volume over R times the moles should not be changing. And since that's equal to the temperature over the pressure, that means the temperature divided by the pressure should not be changing. So what that means is temperature over pressure for conditions 1 should be equal to temperature over pressure for conditions 2. So this is the relationship between temperature and pressure. So in the textbook, they describe each of these relationships, and then they describe how they put those relationships together to make the ideal gas law. But you can also do that backwards, which we just did. We just started with the ideal gas law and explained how if the volume, the moles, and R are all constant, then under some temperature and pressure, when I get that ratio, it should still be the same ratio under some new temperature and pressure. Or in other words, if I increase the temperature, the pressure will go up as well. So when I divide the two numbers, that increase cancels out, right? Let's say I double the temperature. What will happen to the pressure? It will double. So I'd have a 2 on the top and a 2 on the bottom, but 2 divided by 2 equals 1, so it cancels out. So anytime the volume and the moles are constant, that temperature-pressure is an inverse relationship where any factor I multiply the temperature by, the pressure would be multiplied by the same factor. So that sets up this proportion for me. And now I just have to use the numbers. Temperature 1, 298 Kelvin. Pressure 1, 0.8 atmospheres. Temperature 2, that's what I'm looking for. I want to know how high do I have to raise this in order for the container to break, or in order for the container to reach a pressure of 5 atmospheres where it's going to break. So then I just have to multiply both sides by 5 to solve for that temperature. And I get 1862.5, but I only have 3 sig figs, so 1.86 times 10 to the third Kelvin.
So on the test, it'll always be referring it to Kelvins, because sometimes in the back they'll look the answers in Celsius, like in this one. So.
Well, you have to do the calculations in Kelvin.
Okay.
If you then want to convert it back to Celsius, that's fine. Just subtract 273.15. If you give your answers in Kelvin on the exam, that's fine with me. I mean, it's still the correct number. And really, Kelvin is a better measure of how much actual kinetic energy is there anyway, because it relates to that on an absolute scale. The question didn't say what is it in Celsius, did it? No, they gave the initial temperature in Celsius, so that's probably why they gave the final temperature in Celsius, just to keep it on the same scale. But the conversion from Kelvin to Celsius is really straightforward, so